Hi, welcome to this talk on unconditional lower bounds for adaptive massively parallel computation. I'm Anna. This is joint work with Moses Charikar and Liang Tan, both at Stanford. Okay, so let me start with the massively parallel computation model, or MPC. This is a theoretical model that captures the central features of many practical parallel computation platforms, such as MapReduce. In this model, we have an input of length n, which is distributed to a collection of machines. Then the computation proceeds in synchronous rounds. In each round, a machine, which is one of the blue boxes here in the figure, receives some messages from the previous round. It then performs some computation on those messages, and then sends the results to other machines as input for the next round. The key restriction of MPC is that the machines have limited I/O capacity S, in the sense that each machine can only receive or send at most S bits of information in each round. Here we think of S as being much smaller than the input size n. However, the MPC model, as a theoretical model, does not place any restrictions on the computational power of the machines. In other words, the output of each machine in each round can be an arbitrary function on the input messages. The main complexity measure in MPC is the number of rounds it takes to finish the computation. That is, MPC focuses on the communication cost instead of the internal computation cost of the machines. In this talk, we will particularly focus on lower bounds on the round complexity. So from the definition of the MPC model, it seems to have many similarities with the classic model of Boolean circuits in complexity theory. For example, machines with I/O capacity S in MPC look just like the gates with fan-in S in circuits. And the number of rounds in MPC also seems comparable to the depth of a circuit. However, if we look at the literature on the lower bounds in the two models, we will see a variety of techniques that are developed for studying circuit lower bounds, but only quite few for MPC. So a natural question is, can we borrow those circuit lower bound techniques to MPC? However, this seems to be a very challenging task, because MPC is actually a much more powerful model than circuit, mainly in the following two ways. First, as we mentioned earlier, in MPC, there is no restriction on the computational power of the machines. However, in circuit complexity, we usually work with extremely simple gates, such as AND or NOT. Second, and perhaps more importantly, in MPC, the communication pattern is input dependent. This means which machines send messages to which can be different for different inputs. On the other hand, in circuits, the wires connecting the gates are fixed for all inputs. In this talk, we will in particular look at the problem of graph connectivity in the MPC model. So given an undirected graph G with n vertices and m edges as input, we are to decide whether G is connected or not. For the rest of the talk, we will focus on the regime where the I/O capacity S is truly sublinear in the number of vertices. That is, S is n to the power epsilon for some small constant epsilon that is strictly less than 1. For graph connectivity, there is this big O of log n upper bound on its round complexity by direct simulation of classic p-RAM algorithms. On the other hand, the only non-trivial unconditional lower bound we currently know is from the work of Ravgarden, Vasilevsky, and Wang. They show that connectivity takes omega 1 over epsilon MPC rounds to solve. and this bound holds even if we allow an unlimited number of machines. It is widely believed that this lower bound is far from being tight, and in fact, it's conjectured that connectivity requires omega log n rounds to solve. And moreover, the same omega log n round lower bound is conjectured even for a simpler version of connectivity, which is known as the 1 versus 2 cycle problem. So what is this 1 versus 2 cycle problem? As we said, it's a simpler version of connectivity. The input is still a graph on n vertices, but now we are promised that it can only be one of the two following cases, either being a single cycle of length n, or being a union of two disjoint cycles, each of length n over 2. And the task now is to decide which is the case. We can think of 1 versus 2 cycle as a restriction of connectivity, in the sense that the 1 cycles are only a subset of the connected instances, and the 2 cycles are a subset of the disconnected instances. However, as we mentioned before, it's believed that solving this simpler problem in AMPC is already hard. And this is called the logarithmic round 1 versus 2 cycle conjecture, which says that any AMPC algorithm for 1 versus 2 cycle using truly sublinear I/O capacity would require omega log n rounds. And based on this conjecture, there have been a number of conditional hardness results for different problems in the AMPC literature. Now let me summarize the bounds on AMPC round complexity we have seen so far. For connectivity, we have this upper bound of big O log n, and also this lower bound of omega 1 over epsilon. For 1 versus 2 cycle, since it's a restriction of connectivity, the same upper bound carries over. And at this point, we don't yet know a non-trivial lower bound for 1 versus 2 cycle. But, as we will see a bit later, our work will narrow this gap. We will show an omega 1 over epsilon round lower bound for 1 versus 2 cycle in AMPC. It also turns out that we can significantly reduce the round complexity of 1 versus 2 cycle if we consider a stronger adaptive variant of AMPC. In fact, it's known that in this variant, the 1 versus 2 cycle can be solved in only big O 1 over epsilon many rounds. This stronger variant of AMPC is called the Adaptive Massively Parallel Computation model, or AMPC. It's an adaptive extension of AMPC introduced by the recent work of Benezat et al. As we hinted at before, AMPC is a much more powerful computation model than AMPC. In particular, for the 1 versus 2 cycle, the logarithmic round conjecture does not hold in AMPC, as Benezat et al. Gave a big O 1 over epsilon round randomized AMPC algorithm using optimal number of machines in the sublinear I/O capacity regime. In their paper, they also showed significantly improved round complexities for a few other central graph problems. Now let me say a bit more about how the AMPC model works and how it compares to AMPC. The AMPC is originally inspired by the practical low-latency remote direct memory access framework. The key new feature of AMPC is that, in each round, the machines obtain input messages by making adaptive queries to a shared memory, which stores all the messages produced in the previous round. The machines then perform some local computation on those queried messages and write the results to the shared memory. As you can see, the word adaptive means that for a machine in a round, later queries it makes may depend on the result of the earlier ones. So we can think of this sequence of adaptive queries made by a machine as a decision tree. This is very different from the AMPC setting, where we can think of a machine as receiving all of its input messages of a given round at the same time. Another difference of AMPC from MPC is that in AMPC, machines communicate through this intermediate shared memory in between rounds, while in MPC, machines send messages directly to each other. The analog of the I/O capacity in AMPC is that each machine can make at most S queries from the shared memory and write at most S messages in each round, where each message here consists of a constant number of words. I want to remark that these new features of adaptivity and the use of shared memory make AMPC a stronger computation model than MPC. And these features also bring new challenges to proving lower bounds on the round complexity. For one thing, we can simulate any MPC computation in AMPC using the same number of rounds. This also means any lower bound we're able to prove for AMPC is also a lower bound for MPC. Our work focuses on the round lower bounds in this more powerful AMPC model. Before, we have seen an upper bound of big O 1 over epsilon rounds for the 1 versus 2 cycle. Our first contribution is an unconditional optimal AMPC round lower bound for this problem. We show that any AMPC algorithm for 1 versus 2 cycle using machines with truly sublinear I/O capacity requires omega 1 over epsilon rounds. This also implies an MPC lower bound for this problem. But now in AMPC, this is optimal because it matches the upper bound of Benezad et al. Moreover, our lower bound holds regardless of the number of machines involved in the computation, just like the lower bound of Roughgarden et al. Now let's see how this result fits into the landscape of bounds we had earlier. For the 1 versus 2 cycle, before, we had an upper bound of big O of log n in MPC, and an upper bound of big O 1 over epsilon in AMPC, and we had no non-trivial lower bounds. Our optimal omega 1 over epsilon round lower bound closes the gap on the AMPC side, and it also implies the first non-trivial lower bound on the MPC side. This bound mirrors the lower bound for connectivity of Roughgarden et al. We now take a closer look at how our lower bound compares to RVW's lower bound. Our lower bound extends theirs mainly in two ways. First, our lower bound is for the more powerful AMPC model, while RVW's only applies to non-adaptive computations. The power of adaptivity and the use of shared memory pose additional challenges to proving lower bounds. For one thing, the output messages of the machines are now results of decision trees, which can depend on exponentially many locations in the shared memory. The second way in which our bound extends RVWs is that the 1 versus 2 cycle problem is a promise problem. It's a restriction of connectivity to specific promise input instances, which is only a tiny fraction of all possible input graphs. RVW's lower bound does not apply to 1 versus 2 cycle and other promise problems. Before talking about how we address these additional challenges, let me first give a high-level overview of RVW's lower bound proof. This is an application of their more general lower bound framework using a technique called the polynomial method. So to be more precise, they first show that functions computed by small round MPC algorithms can be represented as low-degree polynomials. To do this, they use a family of polynomials to characterize the input messages that each machine receives in each round. This then allows them to connect MPC round complexity to the degree of polynomial representations, which is commonly studied in complexity theory. Next, for this particular problem of connectivity, they show that any polynomial that represents connectivity must have high degree. This allows them to derive the AMPC round lower bound. To get our 1 versus 2 cycle lower bound, we extend RVW's polynomial method framework to the AMPC model, and also for promise problems. This is our second main contribution. Let me first mention how we address the challenges posed by the power of adaptivity and the use of shared memory. For this, we can show something similar to RVWs, namely, functions that are computed by small round AMPC algorithms can be represented as low-degree polynomials. To show this, we use polynomial representations to characterize the new features of the AMPC model. For adaptivity, recall that the adaptive sequence of queries made by a machine in a round can be viewed as a decision tree of depth at most s. We then use the observation that decision trees can be represented by polynomials. As for the shared memory, our solution is the following. In addition to a family of polynomials that characterize the input messages to machines, just as what RVW did, here, for AMPC, we use a separate family of polynomials to characterize the state of the shared memory in each round. Now we turn to the second challenge, which is how we incorporate promise problems such as 1 versus 2 cycle. So to extend the polynomial method to these problems, we need to further upgrade our statement on the previous slide. To be more precise, we show that partial functions computed by small round AMPC algorithms always have extensions that can be represented as low-degree polynomials. For example, connectivity is one extension of 1 versus 2 cycle. Then, as a final step, we show that every extension of 1 versus 2 cycle can only be represented by high-degree polynomials. This is done using standard techniques from Boolean function complexity. And this statement is a stronger version of RVW's statement on polynomial representations of connectivity. And this finishes the proof of our 1 versus 2 cycle round lower bound. Now to summarize, we have seen that the AMPC model, as an adaptive variant of MPC, has much more computational power due to the two new features of adaptivity and the use of shared memory. Then to study lower bounds on AMPC round complexity and also for promise problems, we develop a general framework using the polynomial method, which extends the work of RVW. And then, as an application of this framework, we show an unconditional optimal AMPC round lower bound for the 1 versus 2 cycle, which is a promise version of graph connectivity. Before I end this talk, I want to say that it's still a widely open and very interesting task to consider the hardness of this problem in MPC, or the hardness of graph connectivity in general. And I hope that our work can offer more hints on how we can approach this. Thank you.